In this video, I'm going to explore a little bit the precise definition of a limit, or the more rigorous definition, mathematical definition of a limit. So it's behind me on the board. Let me read it out to you, and then we'll look at some sort of pictures to really describe what this actually means, because it is a little bit different than what you guys are used to in terms of a definition. So as before, we have a function f of x defined on some open interval around x equals a, except possibly at the point a itself. Fine. And then we're going to discuss what it means for the limit of the function to go to L. And so you have in your mind from what we did that, okay, somehow my function is moving and it doesn't really matter what the value is at L. It's just that it's moving towards L from both sides. So that's precisely what we're going to say, but we are going to say it in a more rigorous, precise mathematical way. And what that statement then is it looks something like this. For all epsilon, epsilon being a small number, but not a zero number, it says epsilon greater than 0. So for all epsilon greater than 0, there exists another number, delta greater than 0, so that my function f of x, my values of f of x, are epsilon close to L whenever my x values are delta close to A. Okay? But not equal, right? Because it doesn't matter what happens at the point. That's why there's a 0 over here. Doesn't matter if it has an open circle at the point A or not, or what the value is at A. It just matters what happens around A. Okay, so that's a little bit of a curious definition if you've not seen something like this before. Epsilon and delta are just some kind of small numbers. Often in math we use epsilon or delta to be small numbers, but looking at how you work this out, or what does it really mean, it might not be so obvious. So what we're looking at is we're looking at what's going on in the y and what's going on in the x. So I'm going to pull up some pictures. Let me see if I can share my screen here and get some nice pictures that can kind of make it more maybe visually clear. Okay, so here is one of them. All right, so this actually, the function here, f of x, is square root of x minus 1. And they happen to have taken the point at 5. They called it, this is our A in our definition, and our book uses the letter A. They happen to call it x naught, but fine. Anyway, this is our A. And then the y value at that point is L, which of course clearly is 2, because you put 2 in there, right? Yes. If you put 5 in there, you'll get 2 out. Wrong number. In any case, so what they've done here is they've taken the value of epsilon, my small number epsilon, they've taken it to be 1. So first of all, if I look at my thing here, I've got absolute value, f of x minus L is less than epsilon. So that's telling me that the distance from L to any f of x, right, on either side, that's where you have the absolute value. So right, absolute value, really, if I turn this out, it would be like minus epsilon is less than f of x minus L is less than epsilon, but we don't want to do that. It's kind of ugly, right? We don't need to deal with that if we don't want to. What I want to think about it is I'm looking for all the values within epsilon, all the y values within epsilon of the point L. So my epsilon here is 1, so I go up to 1 on either side of L, right? So that gives me this yellow area. Okay. Now what about delta? Well, here's an example. Let's see what the, okay, well, I don't know what up like that for, but so we can take as an example, and actually this works really nicely, right? Delta equals 3. So delta, now I've gone 3 units from either side of my point A, or x naught, right? And that gives me this other blue box, right? And so the green square is the sort of the square I'm looking at, like the epsilon delta box, okay? And what I want is for any time my x is in this blue region, that the corresponding value of y should be in this yellow region. And you can see it really is quite nicely there. So, okay. Now, if my delta was chosen too big for my epsilon, like this, you can see, okay, it's still fine over on this side, but over here, there's a whole bunch of y values that aren't in the yellow part. So they're not in the green part. That's why the widget has it colored red. It's like, oh wait, this is not good. This delta is too big for that epsilon. Okay, and it turns out if I put it down, if we started at 3, I think. 3, fine. That's really kind of gets them all in there. Now, I can take delta smaller, right? And it's all still good, right? It's just that I don't want to take delta too big. But the important thing is that the value of delta is kind of dependent on the value of epsilon. So see, if I start making epsilon smaller, let's take epsilon like 1/2. Well, that's fine, not quite 1/2. Now my delta equals 3 doesn't work, right? Now, of course, I have to correspondingly make delta smaller so that I'm not overshooting on either side. And so for my 0.6, my delta has to be, say, 2 or less. And that's the whole idea. And this is sort of the thing where you get to the point of the limit. The statement says for all epsilon greater than 0. So not just for epsilon 1, 1/2, 1/3, whatever I got here, 0.2, okay? But you have to be able to take epsilon arbitrarily small and still find a corresponding delta box so that that whole thing is working. Oh, so I didn't even take it small enough. There's a little bit of, okay, let's there. How about that? That works, that works. So that everything is still in the box. Of course, with a nice continuous function like this, this is going to work, right? But I wanted to first show you one where it does work, and then we'll look at an example where it doesn't work. But you can see the idea here, and what do I need to do to actually prove this in a rigorous way? Okay, I don't need a picture with some boxes, right? What I need to do is find the relationship between the epsilon and the delta so that whatever number I put in for epsilon, I can just spit out the number for delta. Okay, that's how the proof will work. And if we're going, we'll go look through some proof, we'll do some proofs in the next video. But just so you know, that's how it goes to show, because my definition says for all, not for some, for all, for every single epsilon. So for every single epsilon, I have to find that. So here's one example where that fails. This is, oh, I have to, I think I have to make my window a little bit bigger here. And I have to warn you something about this. Okay, this is actually, we talked about this function in class, f of x equals sine 1 over x. There's a small error here, which is actually a really big error. They mistakenly wrote sine x over x. They really meant to say sine 1 over x, because as you very well know, we talked about this function too. This function is fine, and it's not the one that's pictured. So they really, like the title, it's sine 1 over x. And that's the one that wiggles all the way, and they nicely put a dot here, which should actually be like an open circle because it's not defined there, and it can't be defined there. So this was one of our examples of the way a limit doesn't exist. And now having this idea in the back of our head that we have to find this box, that will fit, and that box will go as small as you need it, you can see why this isn't going to work. Because, I mean, if my epsilon is this big, right, 1/5, this, and the colors are different because it was made by a different person, but nevertheless, it's the same idea, right? So with epsilon this big, I can take delta really small. That's not working as well as it should. Come on, baby. Let's see if, right. Let me try to reload it. It's going all wonky. See, it just needs to be reloaded. Anyway, so for the picture, for this larger epsilon here, I'm on 1.5 from either way from 0. I can see that everything's in the box. And if I take delta smaller, okay, there at least is going at least somewhat. Still, everything's in the box. The problem happens when I start, so it doesn't even matter then at this point, I can take delta pretty big. The problem happens when I start trying to take epsilon smaller, right? We can't see that now. Oh, come on. If I try to take epsilon, obviously at epsilon equals 1, if it'll do it, come on. It's still okay, right? Because this is 1 and -1, so it's still in there. All right, but if I take epsilon any smaller than 1, I'm going to have a bunch of overshoot. That won't do it. All right, one more time. I'm going to reload it one more time. Now it won't even reload. Oh, there we go. So let's see if we can take epsilon smaller. Because remember, for the limit to exist, I need to take epsilon as small as I like. All right, it won't let me do anything. All right, well, I would, having a day. I would encourage you to click on the link and try it yourself. Maybe you'll have better luck than me. But you can see what's going to happen. This line, if I take epsilon less than 1, this line is going to be like here. Say I take epsilon 0.5, it's going to be right here. And all this stuff above it is going to be in the red because it's no longer in the box. And there's no choice of delta, no choice of this box that's going to make those in the box if my epsilon box is too small. Stop sharing. That's disappointing. Another example, maybe an easier example to see, probably not, but it's probably about the same idea, is our friend, the Heaviside step function, right? But I've got the Heaviside function again at 0. This is going to be 1, and this is going to be 0. Okay, so h of x is 0 for x less than 0 and 1 for x greater than or equal to 0. And the thing about the box is that you have to have them all in the box, right? So anytime I'm going to take epsilon around 0, I could take it around here, or I could take it around here, but if it's small enough, I can't fit them both in, right? I can only fit them both in if it's big. Maybe go like this, right? So if I take epsilon equals 1.5, so now I'm okay. Then I can take delta very small, doesn't matter, and still all the y values are in the box. But if I take epsilon equals 0.5 instead, then what's the limit? Is it the left limit or the right limit or what? Because I have to go around my value of L. No matter which one I choose for my value of L, the ones on the other side aren't going to be in the box. So those are sort of the two canonical examples that we saw about how a limit works or doesn't work or how it fails. And you can see with the definition, it just basically comes to being able to take that box and make it infinitesimally small.